Dear students, welcome to the first session of our Chapter 3 Classification of Elements and the Periodicity in Their Properties. As you know that you have learned this periodic table and all in grade 10. So it's a revision in this chapter, what you have learned before. So we'll see that first, why do we need to classify the elements? The elements are the basic units of all types of matter. Whatever matter you are taking, in that one or the other element is present. In 118, only 31 elements were known, but by 1865 the number of elements had more than doubled to 63. Right now we know that 118 elements are known, with which we can't learn, or it's very difficult to learn the chemistry of all these elements and also their compounds individually. To ease out this problem, scientists research for a systematic way to organize their knowledge by classifying the elements. And not only this, it would rationalize known chemical facts about the elements, but even predict new ones for undertaking further study. Next, we will see the first type of classification, that is Daubernier's triad. The word triad means a group of three elements. So, the German chemist Johann Daubernier in the early 1800s was the first to consider the idea of trends among the properties of elements. But by 1829, he noted a similarity among the physical and chemical properties of these elements, that is, which he was grouping into three elements. In each case, he noticed that the middle element of each of the triad had an atomic weight about halfway between the atomic weights of the other two. And also the properties of the middle element were in between those of the other two members. And he just classified some of the groups. Like first triad he took lithium, sodium and potassium. When he kept together these three elements in a group, lithium's atomic mass was 7, potassium 39. When he just took the average of these two, he got the atomic weight of the middle element as 23. That is Na. Sodium's atomic mass is equal to what? Atomic mass of potassium plus atomic mass of lithium by 2. When he took the average, he got 23, and 23 is the atomic weight of sodium. Like that, when he classified like these elements into three, it was named as triad. The next triad is chlorine, bromine and iodine. Chlorine's atomic mass is 35.5, iodine 127. When took the average, divide by 2, these two when added up and divide by 2, you are getting what? 81.25, which is almost 80 or 81, almost figure is coming for the bromine. So he considered as the triad. The third triad was calcium, strontium and barium. Calcium's atomic mass 40 and 137 for barium. When took the average, we got 88.5 or almost 88 the strontiums. So these are the triads with which we are identifying the elements and learning the properties and about them in that early time. The limitations of Daubernier's classifications were he could arrange only a limited number of elements out of those known at that time in the form of triads. So it was a failure only. The idea of triad could not be applied to all the elements. That's why we can't apply now. Or when the number of elements were discovered, it was not applicable. So the other scientists or the other researchers when done, the next Newland's law of octave came, or Newland's brought the new idea about the classification of elements. That is, the English chemist John Alexander Newland in 1865 brought the law of octaves, and he arranged the elements in the increasing order of their atomic weights and noted that every eighth element had the properties similar to the first element. So he arranged the elements in the increasing order of their eight atomic weights, and when he arranged it, it was noted that every eighth element had the property of the first element. The relationship was just like every eighth note that resembles the first in octaves of music. Newland's law of octave seemed to be true only for elements up to calcium. So this was also a failure only, or we can't apply it for the elements, or when the more number of elements were discovered, it was not applicable. And how he arranged the elements we can see here: hydrogen, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, sodium, magnesium, aluminium, strontium, phosphorus, sulfur. Now you can see here it's almost the musical notes: sa, re, ga, ma, pa, dha, ni. Again the repetition is there from sa. So you can see here the lithium is having the property similar to sodium, potassium, etc. Same way for the magnesium, calcium, beryllium is having the same property. So we are classifying the elements based on the Newland's law of octave in the 1865. Now let's see what are the limitations of this Newland's law of octave. Newland could arrange only up to calcium when there were 56 elements known. After calcium, every eighth element did not possess the properties similar to that of the first. So, in order to fit the existing elements arrangement, Newland proposed or placed two elements in the same position, which differed in their properties, like iron, an element which resembles cobalt and nickel in its properties, is placed far away from these elements. Newland did not include the inert gases because they were not discovered that time. So these were the limitations of Newland's law of. Next classification is Mendeleev's classification. The Russian chemist Dmitry Mendeleev, at an early age of 35, studied the chemical properties of all the elements known at that time and their compounds. When Mendeleev arranged the elements in the order of increasing atomic masses, he observed that the elements with similar properties appeared at regular intervals. This led him to state his famous periodic law, which is named as Mendeleev's periodic law in 1869. The law states that the properties of the elements are the periodic function of their atomic mass or weight. Mendeleev arranged the elements known at that time in the increasing order of their atomic mass in the form of a table, and that table is known as Mendeleev's periodic table. Now let's discuss about the Mendeleev's periodic table. In Mendeleev's table, the elements were arranged in vertical columns and horizontal rows. And there is a name to these two, that is, vertical columns are said to be groups and horizontal rows are said to be periods. And in all, 9 groups were there, that is 1 to 8, and one more is there, that is 0 group. So total 9 groups were there, and they were numbered as Roman numerals. This group 8 occupy what the triads, or 3 triads were placed in that. That means total 9 elements were there in group 8. The 0 group contains the noble gas. As they are stable, they don't have the valency. 0 valency they possess. And there were 7 periods. To accommodate more elements, the periods 4, 5, 6 and 7. 1, 2 and 3 there is no change. 4, 5, 6 and 7 were divided into 2 halves. The first half of the elements were placed in the upper left corner and the second half in the lower right corner of each box. Both gallium and germanium were unknown at the time of Mendeleev. He left a gap under aluminium and a gap under silicon, and these elements were named as Eka aluminium and Eka silicon. Mendeleev predicted not only the existence of gallium and germanium, but also he described some of their general physical properties. We can have a look on the Mendeleev's periodic table. The groups are there: 8, 1, 2, 3, 4, 5, 6, 7, 8, and the 0 group is there. And you can see here the periods 1, 2, 3, 4, 5, 6, 7 periods are there. From 4, 5, 6 and 7, it is divided into two halves, first half and the second half, right? So you can one more thing you can notice that 0 group is having all noble gases. Group 8 is having 3 triads in it. Total 8 elements are arranged here in group 8. Now from 4, 5, 6, 7, it's divided into half we said, right? So this is about what the periodic table of Mendeleev. But it was not applicable because the more elements were discovered and it was not applicable to fix all the elements in these groups properly. So there were defects. And let's see the defects of Mendeleev's periodic table. Hydrogen has been placed in the group 1 along with the alkali metal. So hydrogen, when it was given the group 1 alkali metals properties, it is a gas and all other alkali metals are solids. So how we can prove this thing? So that's a defect. Although the elements in the periodic table or Mendeleev's periodic table have been arranged in order of their atomic masses, but in some cases the element with higher atomic mass precedes the element with lower atomic mass. We know that the isotopes of an element have different atomic masses, but they have the same atomic number. Since the periodic table has been framed on the basis of increasing atomic mass of the elements, different positions must have been allotted to all the isotopes of a particular element, but it was not given. According to Mendeleev, the elements placed in the same group must resemble in their properties, but there is no similarity among the elements in the group or two subgroups of a particular group. When the group 4 or periods 4, 5, 6 and 7 were divided into half shells or half groups in that one, there were no similarity among the elements. In some cases, the elements with similar property have been placed in different groups also. Lanthanides and actinides were placed in two separate rows at the bottom of the periodic table without assigning a proper reason. It was not given a reason why it is kept separate. So these were the defects of Mendeleev's periodic table, which was rectified by modern periodic table. Now let's discuss about the modern periodic law and the present form of the periodic table. In 1913, H.G.J. Musley in England found that when an element is bombarded with electrons in vacuum, X-rays are produced. And also he found that the wavelength of X-rays is related to the atomic number of that element. From this, Moseley concluded that it is the atomic number and not the atomic mass which should determine the position of an element in the periodic table. So, the next one it came as law, that is modern periodic law. It states that the properties of the elements are the periodic functions of their atomic numbers. That means Mendeleev's periodic law is changed into modern periodic law by the arrangement of elements in the increasing order of their atomic number. So, this is from Moseley when he concluded that X-rays are related to the atomic number or the wavelength of X-rays are related to atomic number. Like that, the law came into existence. Now, we know the periodic table is having how many groups and how many periods. Here, you are having a periodic table which consists of 18 groups and 7 periods. Along with that, there is a series of two rows that is said to be lanthanoid series and actinoid series. You can see here hydrogen is separated from the first group. It's just kept little bit upper on the first group so that it doesn't match the same property because hydrogen never resembles the alkali metal. Then the next one you can see 1 and 2 with same color, that means they are having the same properties almost. That means they are the alkali metals. Then group which one is this one? Group 13 to 18 is said to be the p block elements. Group 3 to 12 is said to be D block elements or transition elements. This is what the lanthanoids and the actinoids. Actually, 57 is coming under the group 3. And why it is separated from here? From lanthanum is here. In group 3, the place of lanthanum is here. But after lanthanum, the cerium to lutetium, these 14 elements are not placed in this place. Actually, these 14 plus 1, 15 elements are having the same property. But it's not possible to keep all the elements in one position. So, we arrange them in a particular row which is named as, after the lanthanum it comes, so it is named as lanthanoid or lanthanide series. Same is for the actinoid series also. Actinium's place is in the 7th period of group 3. But after actinium, from thorium to lawrencium, these are having the same property of actinium. It can't be placed here, all the 14 elements or all the 15 elements can't be placed in this place. So it is separated and kept in the next series, which is named as actinide series after actinium. So this way the periodic table or modern periodic table is arranged. Now the characteristics of the periodic table we will just discuss. There are 18 vertical columns or groups and also 7 horizontal and horizontal rows or periods are there in the periodic table. And these groups are numbered from 1 to 18 starting from the left, and it is what the numbers only, not the Roman numerals. Group 1 and 2 elements are said to be S block elements, or we can name it as group 1, 2 and 13 to 17 elements are said to be the main group elements, typical elements, representative elements or the normal elements. These all names are given to these group elements. The elements of group 3 to 12 are named as transition elements. Elements with atomic number 58 to 71 is, that is cerium to lutetium, is occurring after lanthanum, which are named as lanthanoids or lanthanides. The elements with atomic number 90 to 103, that is thorium to lawrencium, occurring after actinium are called actinoids or actinides. So these are the characteristics of the periodic table. Thank you, and we will continue in the next session.